Hi, so in this video we're going to model the motion of a spring mass system, as can be seen in this diagram here. Now, to start off with, let's assume that this block is currently moving to the right. That's a displacement with respect to time. So it's just going past its equilibrium position and it's moving to the right. It will oscillate left, right, but we're looking at the right side of the motion now. So the first thing I'm going to do is I'm going to draw a free body diagram of the system. If the block is moving to the right, then the spring is trying to pull it back towards the left, back towards the equilibrium position. And the force in a spring is Kx, where K is the stiffness of the spring and X is the displacement. Remember, X is a variable. It changes with time. Now, of course, we have the weight, mg, and we have the contact force between the surface and the block. Now, let's derive an equation of motion for the system. So we're going to use Newton's law for this. So we say that the sum of all the forces in the x direction is equal to ma in the x direction. Let's pick right as positive because it's moving to the right currently. Now, the only force, if we look at our free body diagram, the only force acting in the x direction is the kx, which is to the left. We've picked right as positive as our motion is right, because this is the opposite to the motion, so it's going to be minus kx equals m. And in simple harmonic motion, we always call acceleration x with two dots above it. It means the second derivative of displacement with time, which is acceleration. The reason we do that is so we don't confuse it with amplitude, which we also use in this topic. Now, adding kx to both sides, you get mx double dot plus kx equals 0. Now divide both sides by m, is x double dot plus k over m, x equals 0. Let's compare this equation to our characteristic equation of simple harmonic motion. X double dot plus omega n squared x equals 0. You can see it's in the same form as the characteristic equation. This proves that it's simple harmonic. That's the same. That's basically the natural frequency is square root of k over m, x equals 0. Hi, so in this second problem we have a spring mass system with two springs. So the first thing we're going to do is we're going to draw a free body diagram of the system. Now again we're going to say that the block is moving to the right, so x with respect to time. If the block is moving to the right, then both springs are pulling back, trying to bring the mass back to equilibrium. So you've got k1x and you have k2x. We also have mg and we have the reaction force R. Now let's use Newton's law to mathematically model the system. So sum of all the forces in the system in the x direction is equal to m, a in the x direction. Since it's moving to the right, we're going to pick right as positive. So the equation of motion will be minus k1x minus k2x equals mx double dot. Now we have two situations. The first is if k1 equals k2. If k1 equals k2, then we can call them both k. So that becomes minus kx minus kx equals mx double dot, which means we can combine the two together because they have the same value of stiffness. Adding 2kx to both sides, we have mx double dot plus 2kx equals 0. Dividing both sides by m, we get x double dot plus 2k over m, x equals 0. Now let's compare this to our characteristic equation of simple harmonic motion, and we can clearly see that it matches the form, therefore the motion is simple harmonic. Going back to our values of stiffness, if we look at the second situation, if K1 does not equal K2, how do we deal with this? Well, we keep them K1, K2, as the equation above suggests, but we can take common factor x, because both springs have the same displacement. Remember, x is a variable. It's where is the position of your block now from equilibrium. Since both springs are connected to the same block, which is moving with the same acceleration, it's going to have the same displacement. So we can say minus K1 plus K2, taking common factor, of x equals mx double dot. Remember, I've gone straight from this equation here to this equation. This is if they are not equal. Here we made them equal. Here they're not equal. Take common factor of x, it's the same, like I said, it's the same displacement. And then if you expand this out, it goes back to this equation here. We've just factorized. Now, again, let's add this left side to both sides. So we get mx double dot plus open bracket k1 plus k2 x equals 0. Divide both sides by m, we get x double dot plus k1 plus k2 all over m, x equals 0. Again, compare it to your characteristic equation of simple harmonic motion, and you can clearly see that the equation is in simple harmonic form. The natural frequency in this case is the square root of k1 plus k2 over m. Hi, so in this final horizontal spring mass system example, we have a mass with a spring either side. Now, what that means is, let's say our block is moving to the right again, then this spring will get shorter while this spring gets longer. So we need to account for that during our mathematical model. Now let's start with a free body diagram. So as it's going past the equilibrium position, the K2 spring is pulling it towards the right, and the K1 string is pulling it back towards its direction. We also have the mass times gravity, which is the weight, and we also have the reaction force in the y direction. Now let's go ahead and use Newton's law. So we know that Newton's law is going to be the sum of all the forces in the x direction is equal to ma in the x direction. Direction of motion is always positive. So we're going to have k2x minus k1x equals mx double dot. Now we have to account for the extensions. The spring on the left will get shorter because it's getting compressed. So what we do is we say, okay, K2, open bracket, this x here, remember what we said about x, it's a variable. So we have to include the extension within the variable. Now, because K2 is getting smaller, it's going to be extension minus x minus K1. Because K1 is getting longer, the left spring is getting longer, it's going to be extension plus x. You're including the extension in your equation, mx double dot. Let's go ahead and expand the bracket. So we get k2e minus k2x minus k1e minus k1x equals mx double dot. Now, let's assume that k1 in this example is equal to k2. If k1 is equal to k2, then we can clearly see this will cancel with this because it'll be ke minus ke, which is 0. And we'll be left with minus kx equals mx double dot. Combine the two on the left, minus 2kx equals mx double dot. And in the end, we can say mx double dot plus 2kx equals 0. Now, let's compare, well, first of all, let's divide both sides by mass. So we have x double dot plus 2k over mx equals 0. Now we compare this equation to our standard characteristic equation, and we can clearly see that it's in the form of simple harmonic.